let's get started. We're going to do data structures, and we're going to do an introduction to graphs, trees, and all sorts of things. It's kind of a redo of not last week, but the week before. Last week was Thanksgiving. Yeah. So a week before I started talking about trees and stuff and binary search trees, and there was a lot of confusion going on. So I figured I'd hit this topic with a lot more detail. So this lecture is entirely on the tree concept and on graphs. So a quick introduction to graphs, definition of trees, the concept of rooted trees, binary trees, and binary search trees is the focus for today. Starting out with an introduction to graphs. So a graph is nothing more than I wanted to say visual when I first started talking, but it's actually not very visual at all. Graphs and trees are really stored in sort of a list structure. It can be stored in an array, it can be stored in a linked list, all sorts of different types of structures for it. By definition, a graph is an infinite set of nodes with edges between the nodes. And formally, a graph G is a structure V, E, vertices and edges, consisting of an infinite set of V vertices called the set of nodes, or number of nodes, and E for edges, or the subset of the vertice times the vertices. That is, E is the set of the pairs that form an X and a Y, where X and Y are nodes in the V. So let's take a look at this for a second. This is considered a graph. We have a numbered ordered graph, 1, 2, 3, 4, 5, and the vertices are the nodes, which we have 1, 2, 3, 4, 5, and the edges are 1 to 2, 2 to 3, 2 to 4, 2 to 4 in a roundabout way, 4 to 2, 3 to 3, 5 to 4, where X and Y is an edge, and we say that the X is adjacent to Y because they're adjacent in terms of their locations. So 1 is adjacent to 2, 2 is not adjacent to 1, 4 is not adjacent to 3, and in this particular graph we see arrows. So we have a directional graph, which means we're supposed to read it in the direction of the arrows, which is kind of different. We have some graphs that are directional and some graphs that are not directional. In terms of a real-life example of a graph, here's one where the vertices, or the nodes in the graph, are a set of 6 people. So we have John, Mary, Joe, Helen, Tom, and Paul, and their ages are 12, 15, 12, 15, 13, and 13 respectively. And so we could take their ages and we could graph them out in a structure that's going to represent kind of a visual representation in theory of how they relate. So the edges are of X and Y that exist where X is younger than Y. So Mary in relationship to John ends up on this direction, and Helen, Joe, and Paul end up in this sort of configuration. And so we can arrange the nodes in the graph per the order in which they appear in terms of ages. So in terms of the intuition behind the graphs, the nodes represent entities such as people, cities, computers, words, etc. And the edges themselves, the X and Y, represent the relationship between the entities X and Y, such as X loves Y, X hates Y, X is smarter than Y. So we have a relationship that's represented by the edges between the nodes, and the nodes are representing something. In this particular case, the nodes are representing the people, and the edges are the relationships of who's younger and who's older. So directed versus undirected graphs, as I mentioned a few minutes ago. One that has directions has arrows pointing in particular order, and there's an order to the graph. An undirected graph has no actual order in terms of the direction for which it needs to be read. It just shows the relationships. So if the graph of the edges matter, then we show the edge directions, and the graph is called a directed graph or a digraph. In the previous 2 slides, we were looking at directed graphs. If the relationship represents by the edges are symmetric, that means the X leads to the Y leads to the X, there is no special relationship and we're not really showing the direction of the relationship, then we don't need to. And we don't need to put the arrows in. So if the edge, if and only if X is a sibling of Y, then we don't show the directions and the graph is undirected. So here's 2 examples. We looked at directed graphs in the few slides back. These are undirected. So we have 6 people, John, Mary, Joe, Helen, Paul, and Tom, and where the 4 are siblings and the last 2 are not siblings. So these 2 guys aren't not siblings. They're not brothers and sisters or brothers and brothers. These guys are siblings, and so we can say X to Y, where X and Y are siblings, but there's no relationship in terms of one younger or older than the other, and we're not showing direction. Instead, this is what would be considered an undirected. So we don't have any direction here at all. This is an undirected graph. Versus the opposite here, which is this one showing the arrows, meaning it's a directed graph. So the definitions of some of the graph properties. We have this common word called a path. A path in the graph G is the sequence of nodes x1, x2, x3, x4, following the nodes itself, such as there's an edge for each node and the next one is in sequence. So it's a path through the graph. So for each one of the first example graphs, the sequence 4, 1, 2, 3 is a path, but the sequence 1, 4, 5 is not a path because 1 and 4 is not an edge. So in the case of this graph here, we can follow the sequence as long as there's a connection between the nodes. It's part of the path by definition. And a path can apply towards a directed or an undirected graphing concept as well. So if the sibling of a graph, the sequence John, Mary, Joe, Helen is a path, but the sequence Helen, Tom, Paul is not a path. Because Mary, John, Helen, John, Paul, there's no connection between these 2 particular. So this is not a path, Helen, John, Paul. But Helen, Mary, John is a path, but this is not connected, so there's no path between the 2. We also have this word called cycles. So we can cycle through the graph, which is different than pathing. A path is a connection. So a cycle in a graph is a path where the last node is the same as the first node. We cycle through when we end at the same place that we began. We can cycle through this graph here by starting at Mary, going to John, to Joe, to Helen, back to Mary. That would be considered a cycle. So if the siblings here are sequence John, Mary, Joe, Helen, John, the cycle would be the sequence of them all in order, as I just pointed out a few minutes ago. So in terms of connectivity, we can describe the graph as an undirected graph is said to be connected if the path between every pair of nodes is in existence. Otherwise, the graph is disconnected. So informally, an undirected graph is connected if it hangs in one piece. It's disconnected if it doesn't. So formally, this is connected because all of the nodes have some sort of connection together. This is disconnected because we have this piece out here that doesn't, it's missing this connection here. So this would be considered a disconnected graph. This one, on the other hand, is a connected graph. So we can show this relationship in sort of a, kind of a connected versus a disconnected format. In terms of the cycles themselves, the cyclicity of the graph, an undirected cyclic is cyclic if it has at least one cycle. Otherwise, it's acyclic, no cycles. So this has at least one cycle, and a cycle is, remember, starting at the same place that we're ending. And so being able to circle around and actually end at the same place we started. This doesn't. This is disconnected. This one is disconnected, but actually, I should say, it is a cyclic graph because we're starting and ending at the same place. We're just not going very far here, and this one does have a full cycle to it, and it is disconnected. This one is connected, and it's also cyclic because we can go around. This one's disconnected, and it is not cyclic. It is acyclic because we can't do a full circle on it, and we can't actually go between these 2 pieces either. And again, the same concept here where we've got it connected, but we still can't start and end and hit every node without backtracking actually at this point. And it doesn't go in a cycle, I should say. We can't start and end at the same place. So if a tree is connected, acyclic, and undirected graph, the following are 3 types of trees that exist. So in terms of a tree, We're looking at a connected acyclic undirected graph. And these are different kind of concepts. This one here is ordered, so there's a directed one. We have undirected ones as well. And there's three different types of trees that we could actually look at. The concept of a tree usually has a root in terms of the data structure. So a rooted tree is a tree where one of the nodes is designated as the root. We start out with the root, so only one root in a tree. It's kind of like the starting point of a linked list where we have head. So we can actually have a head and then we can have a root, actually, as following if we wanted to. So the rooted tree is a hierarchical structure. The root is on the top, followed by nodes that are adjacent to the right to below, followed by nodes adjacent to those, and so on until we build it. Here's some examples of rooted trees. We have an unrooted tree over here where we don't have a root, nothing's on the top, although we could turn this on the side and sort of turn it into a rooted tree. But this is generally the rooted idea, where we have a root on the top of number one and it leads off to child roots. And then the root essentially is a node, just like these other nodes in the diagram here. And with the biggest difference is that this is the number one node. It's the starting point. So this is really not a root because it's not at the top. We could say number 9 was a root, perhaps, but it's not the starting point. So it's not generally considered a root. So here's some more tree-related concepts. The nodes that are adjacent to X and below X are called children. So these are child nodes. And this is the parent node. And so every child's node refers to parent nodes, and parents can be child as well. So the node that has no children, down here on the bottom, is considered a leaf. And descendants of the node are itself its child. Their children are all the way down the road until you make it to a leaf. So you have a parent, a child, a child, a child, a parent, all the way down to leaves. Ancestors of a node are itself its parents, its grandparents, and all the way back up to the roots. So the root is the parent of everybody, essentially. The depth of the tree can be counted by the number of edges from the root to the nodes. Example, 1 edge, 2 edge, 3 edge, 4 edge. This would have a 4. The depth of the tree would be 4. Number of edges, 1, 2, 3, 4. The depth or the height of the rooted tree is the depth of the lowest leaf, so the height of the tree is 4. And node 10 is at level 3, 1, 2, 3. Or you could just simply start counting the nodes starting with 0, 0, 1, 2, 3. Or you could count the edges, 1, 2, 3 edges. So binary trees, this is what I was talking about in the last lecture, and everyone was kind of confused. Or not confused, but there's a lot of brand new exposure to it. So a binary tree is a tree with 2 nodes, essentially. So a tree, or 2 nodes following 1 node. A tree is a binary tree if every node has at least 2 children, or excuse me, at most 2 children. Can't have more than 2 children. It can have 0 children, 1 child, or 2 children. So this is not a binary tree because we have 3. We have root node number 1 leads off to 1, 2, 3 children. And this one is a binary because 1 leads off to 3 and 7, so we have 2 children, 8 and 9, 2 children. We can have 1. We don't have to have, everybody doesn't have to have 2. And then we have, in case here with number 8, you don't have to have any children. So 0, 1, or 2 makes it a binary tree. 3, no binary, not a binary tree. We care about binary trees because we can take a binary tree structure, traverse it, and end up being able to apply an algorithm to it. It gives us a nice little searching technique, very similar to a binary search on a list. So it lends itself, the binary tree itself lends itself quite well to data structure that can be used for searching. So the child of any node in a binary tree are ordered into its left child and then to its right. So we always we always go left to right. So when we add a node to the tree, in this particular case, if we started with number 1, we would add number 3, then we would add number 7. So we would add left to right. The node can have a left and a right child, a left child only, or a right child only, or no children at all. So the tree is made up of the left node, or the X node, and all of its descendants is called with the left tree of x, and then the right tree are defined in a similar way, but it's usually done in the next sequence. So we could go number 1 to number 3 to number 7 to number 8 to number 9 to 10 to 11 to 12. So we always read it left to right. Here's a graphical view of the binary tree nodes. So the binary tree itself, the node contains 3 different parts. In order to really understand this, you'd have to basically go back to the concept of linked list and think this is a doubly linked list, actually. It's identical to the doubly linked list. And if we remember linked lists, each node is carrying a piece of data, and that's this item right here. It's data. And then in a linked list, we have a next or we have a previous. In a singly linked list, we have a node that's going to hold data and then a next, and then a data, next, data, next. So each node knows about its next. We turn that singly into a doubly, and now we have the node with next, and then we have the previous. So we have 2 pointers along with 1 piece of data that's associated with each node. So following that same trend with a doubly linked list, we have a tree. A tree is a doubly linked list. Think about it. But the doubly linked list, instead of a previous and a next, is a right and a left. So each node knows about the right and the left that is associated with it. So the pointer to the left child and a pointer to the right child exists for each one of the nodes. So in practice, a tree node will be shown as a circle where the data is put inside of the circle, and the node is labeled if there's a label for it. And so we have data that leads to this number, and then we have this label that might be associated with it. So here's some sample code as to an implementation of a tree node, and this should look very familiar to you. It's the same as a doubly linked list, actually. And this is written in Java, and actually this is written in C++, my apologies. And what we're looking at is nothing more than the implementation of a tree node, a left, a right, and these are pointers, actually. If you're going to do this in Java, it would look very similar, minus the pointers, essentially. But we would have a concept of the node. We would create nodes for and pointers to the nodes for the left and to right members of the same node. I'm going to kind of skip through this because we don't really need to see the C++ implementation of it, especially when all the other examples you've been working with have been in Java so far. In terms of the binary search tree, this is a special form of the tree. So it's a binary search tree is a binary tree where every node holds a data value. So it's called a key. So every node is holding a value. For any node x, all of the keys in the left side of the tree of x are smaller than or equal to the key of x, and all of the x's on the right side of the tree are larger than or equal to x. So we put the smallest value on the left, the larger value on the right, and x is the parent node. So here's an example of a binary search tree. And so if we wanted to create this structure, let's say we had a list of items, and if we wanted to create this structure, we would kind of build the tree and then use the tree as the data structure to be searched. And so when we search it, we can find items by going left or right. Just like the binary search is done on a list, we can apply the same logic essentially to the tree. So if we started with 15, we would go, well, 8's less than 15, it belongs here. 20 is larger than 15, it goes on the right. And then we go from 20, well, 27 goes on the, 27 is bigger than 20, so it goes on the right. And then we have, well, 22 is smaller than 27, so it goes on the left. And 30 is larger than 27, so it goes on the right. And we can kind of build the tree using that, is it larger, goes on the right, if it's smaller, goes on the left kind of structure until we have built the tree. And then when we traverse it, we're going to search through the tree with that kind of fashion. So here's that same tree, and what we're going to do is kind of apply a little search. So to search for a number b, for an a number b, compare b with the root. And so here's the root 15. So if b is equal to the root, so let's say we're looking for the number 15, and we started the root, well, we found it, we're done. We don't have to search anymore. Let's say we're looking for the number 11. And so we look at the root, and we go, well, is 11, is it larger than? So if 11 is larger than the root, you go to the right. If 11 is smaller than the root, you go to the left. So we started here with 15, and I'm looking for the number 11. And I'm going to go to the left, because 11 is smaller than 15. Takes me to 8. And then I go, well, is 11 larger than 8? Or is it smaller than 8? Well, it's larger than 8. And then I found it right here. I found 11 right here. So you repeat the process, and this is how the algorithm is implemented. And although, you say, well, binary search tree, it sounds like a complicated concept in general. But it's actually quite simple if you think about it. So you repeat the steps till you find the node that you're looking for. So if we try it with 12, here's our number 12 down here. And I come up to 15 because you always start at the root. And I say, well, is 12 smaller than or larger than 15? It's smaller. So I'm going to go to 8. Well, is 12 larger than 8? Yeah. So I go to 11. And you go, well, is 12 larger than 11? Yep. And here's, lo and behold, I found 12. So it's a pretty reliable way of searching through the tree to find. That's basically how a binary search works through the tree. So I'm going to skip the C++ implementation of that. So trees are great if you build them after you already have your data. As you could possibly imagine, if I have all this data already, I can kind of go through the data and build the tree in this sort of order, going left to right, and just take each item and populate it into the tree. But how often does that happen and the data never changes? So usually you're going to need to add items to the tree, take items away from the tree, manipulate the tree in some fashion in order to get at the information that you're looking for. And that's where these algorithms kind of get interesting. So to insert into a binary tree, we're going to insert a data type B into tree T. We search for the position of B. Where should it go? As if it were in the tree itself. So we find, if we were going to look for the item, let's look for where it's supposed to be. So we do the search the same way as if we were trying to find the item. And the position is in the left or right child of some node X. We create the new node, and then we assign it the address to the appropriate pointer field of X. And then we assign B to the data field of the new node. So if we were to say, let's say we're going to search and we're going to insert the number 25 in this particular example. Here's the before the tree. Let's say 25, let's say 25 is bigger than 15, so I'm over here. 25, well, it's bigger than 20, so I'm over here. 27, that's less, 22. And I go, well, 25 is still higher than 22. Well, it should go right here. So we know it should go on the right instead of the left child. We don't actually draw an empty child in here. We just draw it to the right, and we insert it essentially. So that's where it would be inserted into the tree, and that's a pretty easy insertion. However, what if it belongs right here or something? What if the number was 9? That would be right here. So 9 smaller. Well, 9 smaller it would actually end up with 10. So our order would kind of be messed up a little bit in that case. So to delete an item, and we would just basically, if that were the case, just to finish that concept, we would have to rearrange, just move an item down to insert it where it's supposed to be, and then add the 10 underneath the 9, if that were the case. So to delete an item from the binary search tree, we would use a very similar fashion. We'd search the tree to find the item. If it's not found, we would return. If it is, we call X the first node found to contain B. If X is the leaf, we remove X. If it's at the leaf, it's easy, we just remove it, and then set the appropriate pointer to null. If X is only one of the child, let's say for child Y, we remove X, and then the parent X becomes a directed parent of Y. So if X has 2 children, then we go to the left tree, and then we find where the largest node is, and then we call that one Y. And then the node Y can be found by tracing the rightmost path until the end. Note that Y is either the leaf or it has no children associated with it. And then we copy, I'm going to see an example of this in a few minutes. Copy the data field of Y onto the data field of X, then delete the node Y in a manner similar to step 4. So, I thought the code was in there. But what you're doing, actually I have code coming up later on that's going to show you the deletion. However, what you're doing is essentially the same concept where you have to shift to fill in the holes, because you can't delete a parent node and leave its children hanging. So you have to move one of the children up, and you're going to move the Y up because it's going to be bigger. So the tree traversal techniques, we have what's called a heap, and I'm going to get into that concept in a few minutes. So tree traversal concepts are very applicable to the concept of the binary search tree. Techniques for pre-order, in-order, and post-order are applicable, as well as the concept of full trees, almost full trees, and heaps, which I'm going to cover next. So binary tree related definitions. So the child of any node in a binary tree or ordered left to right. So a node can have a left or a right child only, or a right child only, or no children at all. So it can have a left or right or nothing at all. And the tree is made up of a left child is the X, and its descendants is called the left subtree of X. The right subtree is defined similarity. We've seen this a few minutes ago in the beginning. We've actually seen the code already as well. So if we traverse it, the traversal is the process of visiting every one of the nodes at least once. We traverse the trees to problem solve. So if I wanted to know, as an example, how to get from point A to point B, and I'm a GPS program, I'm going to take the city maps of San Jose or wherever I am, put it into a binary tree, maybe, or put it into a tree or graph structure, and then traverse it. And traverse it means to follow the path. So I can figure out how many paths there are from point A to point B and select the shortest path if I want to. So that's kind of a time-consuming way of doing it. It's actually called a traveling salesperson algorithm, where you calculate out each one of the paths and you figure out, well, what's the shortest route? And it's actually kind of sort of similar to what your GPS programs are doing, using different algorithms to calculate it, obviously. So visiting the nodes entails going to some processing at that node. But then describing a traversal strategy, you're concerned with the processing and what you're processing. So there's three recursive techniques for binary traversal. Because binary trees as a structure lends themselves to better traversal. In other types of structures, you might end up with dead ends. You know, how many people have, actually just gotten in your car and started driving down streets? You're sort of traversing a graph, and then you hit a dead end. You go, or a one-way street. And you go, well, what happens here? You got to turn around, backtrack. So if you build the map, so it's a pre-ordered kind of configuration, then you can build a strategy for searching it, so you'll never go down the wrong path, essentially. But it would be nice if you're, actually, as another feature of your GPS system might be one that says you're going down the wrong path. You're never going to make it. That might be a nice feature of a GPS program, because it should be able to figure that out if it knows the map, if it's watching where you're going. So, but it does, I like that, recalculating, and then you go into it. It knows you're going down the wrong path, so it recalculates. So there's three recursive techniques that are used for binary traversals. In each one of the techniques, the left tree is traversed recursively, then the right tree is also traversed recursively, and then the root is visited. So what distinguishes the techniques from one to another is the order in which those three tasks are performed. So here's our three different options. We have a pre-order, in-order, or a post-order option. So in the pre-order, the root is visited first, or before, or pre the subtree traversal. So you start at the root, visit the root, traverse the left subtree, and then traverse the right subtree. In an in-order, you go left, root, right. So you do it in order, essentially. You start with the left, you go to the root, you go to the right. In a pre-order, you traverse the left, you traverse the right, then you go to the root, and you hit the root last. So a post-order is hitting the root last, pre-order is hitting the root first, in-order is getting it in the middle, essentially. And I have some diagrams here to show you this. So assuming that the visiting a node is printing its label, as an example, the pre-order starts with 1, starts with the root, goes 1 left to right, 1 left to right. So we have 1, 3, 5, 1, 3, oops, we're going to the left, 1, pre-order, 1, 3, 5, 4, 6, because we're visiting the root first, and then we're going left to right. So the root to the root to the root to the left, right. The in order would go 4, 5, 6. 3 to 1 to 8. So we're hitting it this way with the root in the middle. The post order hits the root last. So we have a 4, a 6, a 5. So we're hitting the root last. And then we have a 3, 8, 11. So we got the root coming in at the last, the post order. 3, 8, 11, that is correct. Okay, so assuming that we're visiting the node and printing the data out, and here in this particular example we have the order in which the pre-order would go 15, 8, 2, which is pretty much the same example. I'm just going through another example of it. 2, 3, 6 for the in order. 2, 3. Where's my 6 on here? 2, 3, 6. I don't see a 6. Oh, here it is. Here it is. I'm reading it wrong. 2, 3, 6. If I'm reading it this way, here we go. The in order, putting it in the middle. The root ends up in the middle. And then the post of a 3, 7, 12. If we read it, we'd print it out 3, 7, and then 12. Nope. 3, 7, 6. I'm sorry, 3, 7, 6. Reading the root last. So, are you going to visit the root first? You're going to visit it in the middle. Or are you going to visit it last? Or your pre, in, and post order. So, and here's some sample code for implementing it. What you do is basically take that logic, write it out into a method, and then do a pre-order, an in-order, or a post-order type method call on the node. So the code is visited, it's processed depending upon the application, and then how you build the tree is going to be how you traverse the tree, what you're using with the tree in order to get the logic out of it. Because trees are essentially used for problem solving, and what we're trying to do is figure out, well, what is the shortest path? Or what is the direction we need to go in? Or where's that piece of item, that piece of data that we're trying to find in the tree? So applications of traversing a sorted binary search tree, you observe the output of the in-order traversal, and examples of the last 2 slides that we just looked at. You know, is it sorted? Yes, it is sorted. So there's no coincidence that it is sorted. It has to be a sorted list. It's just like in the concept of a binary search on a list. If we have a list of items and we put it in ascending order or descending order, we can find the midpoint, and then we can go left, right, and then find the midpoint of that and search as the number higher or lower, which is essentially the same search strategy. So the tree itself actually needs to be in order. So as a general rule, if the output of the keys or the data of the nodes of the binary search tree, using an in-order traversal, the data comes out sorted in increasing order. So the data will always come out in an increasing order. So we have 2 kinds, or other kinds I should say, of binary trees. The full binary tree and the partial, or the incomplete. So the full binary tree is a tree in which there are all leaves that are all on the same level, and every non-leaf has at least 2 children. So the first 4 full binary trees, as an example, all the leaves come out at the same level. Everybody has at least 2 children, which means it's full. This one is full, even though we have a node. We have no leaves. This one we have 2. This one, everything is balanced. And in fact, going back to the concept, it is called a balanced. But in terms of binary search tree terminology, it's really referred to as a full binary tree versus a balanced. Examples of non-full binary trees. So these trees are not full. Do you know why? This one's missing its right child. This one's missing its left child. This one not all of the leaves come out to the same spot. This one is left heavy, obviously. So each one of the trees is not balanced by concept. So I cannot say that word. Canonical labeling of full binary trees. So the label of the nodes here, looking at essentially the labeling of the nodes. Labeling of the nodes allows us to take the tree, flatten it out into a list, and then take the list and treat it like a linked list, actually, if we wanted to. So the labeling of the nodes from 1 to n, from the top to the bottom, so going left to right as well. So number 1, the node of the root is always 1, and then we always start left to right, so we always get 1, 2, 3. So 1, 2, 3, 4, 5, 6, 7. So we end up going left to right, level by level, node by node, which makes it kind of interesting. So the relationship between levels of childs and parents is going to be 2i plus 1. So it always increases to the right. If we keep that logic in mind when we write the algorithm to read it, we know the order, essentially, of the labeling. So we have an almost complete binary tree example here. An almost complete tree, an almost complete binary tree of n nodes for any arbitrary non-negative integer n in the binary tree, made up of the first n nodes of a, there's that word I can't say, labeled fully binary tree. As an example, these would be incomplete. They're not, well, they're complete binary trees if labeled correctly. So we have the 1, 2, 3. These are just essentially more examples of the same concept of an almost complete but incomplete. So whether it's almost complete or whether it is complete depends on the numbering of the leaf nodes, as mentioned before, and the numbering applied. So we have 1, 2, 3, 4, 5. We just take what we have and we apply the numbering to the nodes. So each node gets a label and it goes in the same type of order, level by level, ascending, smaller on the left, larger number on the right. So the depth and the height of the full trees and the almost complete trees, by definition, the height or the depth of each of such trees, we can calculate the efficiency of the tree in terms of its complexity, or the O notation, log n. And I'm not going to go through the calculation for this because this is not an algorithm course, but if we were considering the concept of algorithms and we were thinking about the efficiency, we would want to build the tree to make the most efficient algorithm for traversing it. And in that case, we would probably come up with a full tree. So almost complete trees, the proof is left as an exercise if you'd like to do it. The full tree calculation is given for you in this slide set in terms of how to calculate that out. And basically what you're doing is just counting the number of nodes. So the number of nodes from n to the beginning of the tree to the end of the tree gives you the complexity that you're going to be interested in knowing in terms of the efficiency of the algorithm for searching it. So, and just keep in mind, any tree you're using is going to be much more efficient than a lot of the other data structures that you might be exposed to. In fact, if you keep a binary tree in a linked list format, or even in an array, and you do binary searches on it, you're going to end up with a faster algorithm in the long run versus doing a linear search or one of the other types of searches. It just lends itself to a more efficient searching technique because you're always cutting your problem space in half every level you go down. So here's an almost complete example as well in terms of the labeling. The same labeling is inherited from the full binary tree as applied to the almost complete binary tree. So the same relationship holds true. It's the same format. You're just applying it to an almost complete versus a complete tree. So in terms of the full tree itself and the almost complete binary tree itself can be represented in terms of an array by flattening out all the items. So if you've got the labeling, I'll go back to this picture here. If you've got the labeling of this, don't these look like index values to you? So you can, if every node only has one label and there's an order to the node, you flatten it out in terms of the number of the nodes, and you've got an array, you've got a linked list, you've got a tree that can be flattened out and turned into any type of list structure. And you would essentially use this from a computer science perspective. This ends up being the data structure that you're storing, whether you're using a linked list or an array. In this particular example, we're going to turn it into an array. So it's represented by array A of the same length as the number of nodes. And so AK is identified by the node of the label K. So this A0 would be the root, A1 would be the node on the left, A2 would be the first node on the right, and then you would continue with the same logic. The advantages: no need to store the left and the right pointers. If you remember at the beginning of the slide set, I basically gave you the node implementation for linked list and called it a doubly linked list. Well, we've got the data, we got a pointer to the left, a pointer to the right, and each one of the nodes is containing all that data. A lot more storage, as the data structure itself is taking up a lot more room. Might actually, if it's a linear list that's sorted, it's probably better to put it in an array structure, actually, if you know the order of it, if it's already sorted. For a non-sorted list, then it makes more sense to put it into a linked list structure and keep the left and the right. But arrays are a little bit easier, especially if you're working with an index sorted list. So it takes up less memory. Direct access to the nodes. If you want to know what a node, you just access it by its index value in the array. You can get to the node quite easily. And here's a representation or illustration of the array representation here, where we've got the items 15, 8, 20 that are into the node orders. So we can notice, you can read the bottom here on your own, but you're noticing you can find the parents, you can find the children by their index values. So it really lends itself quite well for storage. And you're working at it from an abstract concept, so going back to what I originally said, we don't have a real visual unless you draw the visual out yourself, but you're using it like a visual tree, but you're not really creating, you're really creating a list essentially, but you're traversing it like a tree. So it's kind of an abstract concept. And that's one of the things that a lot of undergraduate computer science students have a hard time with when they start learning data structures. You know, where does this tree come from? And all of a sudden the word tree scares them, but list, they're familiar with lists from arrays, but here we're looking at a tree that's implemented in the form of an array, and we're going to use it just like an array, essentially. So adjusting for the indexes, noticing that the previous slide, the nodes labeled start with 1. Well, we don't have arrays that start with 1, we have arrays start with 0. So we just start our numbering with 0. So C, C++, Java, everything arrays start with 0 instead of 1, so we just adjust it. So by way of handling a mismatch is to adjust the order, start with a number 0 instead of 1. So applications, we have the concept of the heap. And a heap itself is an almost complete binary tree where every node holds a data value. Well, we're going to hold data anyway, that's why we're creating this. And the key of every node is less than or equal to the key of the children. So it's an ordered heap is nothing more than and this is the min heap in this particular case because we have the minimum values on top. So it's just essentially creating an order in terms of the structure we've already been looking at. Note the maximum heap has the same definition except the keys of the node is larger than or equal to the keys of the children. So it depends on the order that we're going to create it. Here's an example of a minimum heap, and you notice the big numbers are on the bottom and the small ones on the top. So it's going minimum on the top roots the minimum value of the tree. Looks like a binary tree. It is a binary tree. So a heap is nothing more, and a min heap is nothing more than a binary tree that is sorted with the minimum value on the top versus the maximum. If we turn it around, put 33 on the top, we'd have a max heap on this particular example. So operations that can be performed, we can delete the minimum value, and then we can return it. The operation is called a delete min. Insert a new data value in it. This is helpful when we have, sort of like a queue or stack. Or, we talked about stacks and queues before. Last one in, first one out, first one in, last one out, all the different ways of sorting it. Well, min heaps and map heaps are used for the same purpose. If we got a big old item we want to take, maybe this is aging. Number 5 has been waiting the longest time. As the number keeps going down as they get closer to their turn or something, and then we can remove that one. Let's say if that's the next one. So in terms of the application of heap implementations, it implements a priority queue. So we can take a priority queue implemented sort of as a min heap, in which the queue that orders the entities not on a first come first served basis, but on a priority basis. So the items of the highest priority are at the head, and the lowest priority are at the tail. Tails are the leaves, the head is the root. So another application might be sorting. So in terms of deleting the minimum and the minimum heaps, we just remove the root and we move everything up. We move it up in a kind of a pre-configured fashion. So the value of the min heap is at the root. So it's kind of easy actually. So the functionality that we're doing to remove items and then to insert items in these particular heaps makes for a faster insertion, a faster deletion, because it's ordered to optimize that kind of functionality. So to delete the minimum, you can't just remove the data value of the root because every node must hold a key that's associated with it. So instead you take the last node of the heap, move it to the key of the root, and then delete the last node. So you delete the last item. But now for the tree is no longer a heap. So once you start adjusting for removal and for insertion, you have to reheap it, essentially, which means that you have to rebuild the heap to create it again. So if you don't have a heap, you have an almost complete tree, but the root value is no longer less than or equal to the keys of the children, then you rebuild the heap. So here's the case here. Which this tree we want to remove the minimum. Minimum is 5. If we take 5 off, we have to move an item up there. We're going to move one of the children items, 12. We put 12 on the top now. Now we got to reorder it essentially. Otherwise, we're going to end up with an unbalanced heap essentially. So in the first stage, we would do that. So to restore the heap, we bring the structure back to its heapness, its happiness. So we restore the heap. Swap the root key with the smallest child, and then proceed down until you have all of the children in the correct order, keeping the smaller than or equal to child on the left and the larger one on the right. So illustration of restoring the heap in this particular case. 8 is now the smallest value, so we move 8 to the top when we replace that with 12, and then we end up rotating 12 so it's above 11. So we keep moving stuff down. So this is the correct heap that would be created from that. So in terms of efficiency, going back to that comment on a heap, it's nice because we can easily remove, but we end up having to restore the heap. So there's a little cost-benefit analysis you can perform on the data structure as to whether or not it would make a good application, or a good structure to use in your application would be calculating, well, what's it going to cost in terms of efficiency to restore the heap if we're going to keep it in a heap. And if you're not really removing items and you're just searching it, or you're removing in a particular order, then it might make sense to use the heap, and it may not be making very much sense to use the heap eventually. Time complexity of the insertion of the delete minimum. Both operations take proportionally to the height of the tree, which is going to be the search space. So how big is the tree? Depends on how long is it going to take. It's going to affect the running time of the algorithm. When restoring the heap, the bug moves, and the bug is the change that needs to be made. Moves from level to level. In the worst case, it becomes the leaf in the delete minimum, or the root in an insertion. If it's the root and it has to make it all the way up to the top, it's going to take longer. It's not going to be very efficient. So each move in this to a new level takes constant time. So it depends on the size of how many levels the insertion takes as to how the running time is going to work. Therefore, the time is proportional to the number of leaves. So inserting into a minimum heap. Suppose you want to insert a new value x into the heap. You would create a new node at the end of the heap. Put x at the end of the array. If x is larger than or equal to its parent, then you're done. If it's a big item and you're putting it on a min heap and you're adding it to the end, you're all done. That's pretty easy. Otherwise, you got to restore the heap. You got to move it up. So repeatedly swapping it with the parent until x reaches the root. It becomes larger than or equal to its parent. So I'm not going to go through the C++ code for the heap. However, you can use this as an example if you wanted to implement it. So what I just gave you was kind of the basic structure of graphs, how graphs turn into trees, how trees turn into heaps. And hopefully what that will do is clarify some of the terminology for you in terms of understanding the data structures as a whole. And the implementation, as you could probably imagine, is kind of trivial. You can implement heaps, you can implement binary search trees, binary trees, graphs, using everything you've learned so far in the course. You can use arrays, you can use linked lists, doubly linked lists, you can have many different selections. What's going to give you the best implementation is going to basically be representative of how much time it takes to search it, sort it. Basically it's dependent upon what you're going to use it for. If you've got a sorted list that you're going to use and you're going to do a lot of searching on it, then it's probably best to store it in a binary tree kind of fashion and search the tree every time, and it's going to be faster. Or if you do a binary search on a list, it's going to give you about the same efficiency according to how you're storing it usually. Alright, so that actually concludes the last lecture for the data structures course. No more boring material. No, it's not boring. No more data structures material. So next week, what we're going to have is called the final exam review. And the final exam review is going to tell you everything that's going to be on the final exam. And the final exam, I can tell you, is going to be 25 multiple choice questions. And the 25 multiple choice questions are going to come from everything I've covered throughout the entire course. So next week I'm going to bring in the exam, and we're going to go through it question by question, and you're going to know what to study essentially, which is going to hopefully help you. Well, hopefully will help you. And unless you have any questions, comments, or concerns, we are done for today. Questions? No, we're done. Enjoy the rest of your day. All right. The final exam is on the 12th or the 14th. Or it's on the 14th for this class, but you can take it on the 12th if you want.